Energy resources then. You've talked about this a great deal in the past. Energy resources can be broken down into renewable and non-renewable. Non-renewable would be fossil fuels and nuclear fuel, for example. Fossil fuels being coal, oil and natural gas. So we make electricity using our renewable and non-renewable energy resources, and for the most part what we do is boil water to make steam, to drive turbines, to drive generators. That's the case for coal, oil, natural gas, biomass to an extent, and nuclear. So how long these will last depends on how we use them, really. Here is a generic power station. So we take our coal, our oil, our natural gas, we burn it, we boil water, we make steam. The steam then drives turbines which connect to generators which make electricity. More of that when we come to it in year 11. Nuclear is very similar. There's no burning involved. The nuclear fission that occurs naturally is controlled, and the energy that is released from the fission heats a coolant which boils water, which makes steam, which drives turbines. So really everything from here across is the same for your coal, oil, natural gas, nuclear power station. It's how you boil the water that is different. One of the big problems, of course, with fossil fuels is that you release carbon dioxide when you burn them. Carbon dioxide then traps the sun's infrared energy to some extent in the atmosphere, and so the Earth warms with all the consequences that entails. You have sulfur dioxide that comes from the burning of oil and coal as well. That then dissolves in the water in the atmosphere, making sulfuric acid and falls as acid rain. So these are serious consequences in the use of fossil fuels, and they're going to run out anyway. Renewable energy resources then, there's lots of these. We have the sun, which then is used by photosynthesis by plants to produce trees. They produce fossil fuels, but also, of course, we can produce biomass. We can cut the trees down and burn them. We have the wind, of course. We have geothermal. We have tides. Geothermal is a natural thing. Tides, twice a day we have high tides and low tides, and we can use them then to produce electricity. Wind power, well, that's a free energy resource, but it's unreliable in the sense that the wind doesn't always blow, and if it doesn't blow, you don't make any electricity. Wave power is great, except that we tend to break the things we put into the waves to try to capture the energy, but it's a really promising energy resource, again, completely free. In terms of the energy resource, of course. Tidal power, well, if you trap the you trap the water at high tide and you let the water flow through the turbines at low tide, you can make electricity. And your tides are very predictable, so you know exactly when you're going to get to make your electricity each day, which allows it to be more reliable. But still, you're making electricity for 2 periods a day, You could make it as the water flows into your reservoir, but as the water flows out, you can drive your turbine. But there are serious consequences for building tidal barrages. You flood land to do it, as you do with hydroelectric power stations to come, which changes the ecosystem significantly. And it's very, very expensive. Hydroelectric power, you have a dam, so you build a great wall across the mouth of a river. You build your power station into your wall. The water flows out of the dammed reservoir, the upper reservoir, and drives the turbines. And you can also bring that water back up. You can pump the water back up the hill. It's not very efficient, but you can pump the water back up the hill and do it again. So you can store excess electrical energy by using it to pump water up the hill and then get it back by letting the water run down the hill again. And that's called a pump storage system. We have one of those in Wales, and they buy excess electricity from the national grid and use it to pump water up to the top of a mountain. And when the national grid needs water or needs electricity in a hurry, they can ask this power station to deliver it, and they can produce electricity very, very quickly. Geothermal energy, well, down in the depths of the earth, the nuclear reactions produce a lot of heat. And we can, by pouring cold water, pumping cold water into those hot rocks, we can get hot water or steam out, depending how deep we go. We go deep enough, we'll get steam, and the steam can be used to drive turbines. The process of doing this is very expensive if you have to drill for it. Places like Iceland have the hot water coming to the surface, and Iceland produces its electricity and its heating using the water heated by geothermal means. So you don't have to pay for the fuel, it's totally renewable, but it only works in particular places economically. Solar energy, of course, you can do this on a small scale on your house, you can do it on a large scale. You trap the solar energy and you can either make hot water or you can make electricity. It's generally small scale in places like the UK, and it is of course unreliable because you don't know when it's going to be sunny. But you can make solar furnaces as well. So you're trapping the solar energy using mirrors, and you're using it to boil water to make steam. So you can do this on a large scale as well. Here's a solar furnace, mirrors focusing the light onto your water reservoir making steam. Biomass, well, as I mentioned, that could be trees. It's any kind of organic matter. So it could be animal waste being used to produce methane. It could be trees being burnt to produce heat. You obviously burn the methane from the rotting waste or the animal waste and use that to drive turbines. You can ferment sugar to make ethanol and then use the ethanol as a fuel. Alcohol burns very well. So that's biomass, really. Nuclear fusion, well, nuclear fusion is how stars produce their energy, and if we could do that on Earth, that would be great because it gives us a lot more energy per kilogram, a higher energy density, and we don't have the long-term, long-lived nuclear waste. It's short-lived, there's not very much of it, so it's much, much safer. Nuclear fusion, if it all goes horribly wrong, just stops, whereas nuclear fission will get out of hand and explode. So nuclear fusion looks great. You take two isotopes of hydrogen and you smash them together so fast that the nuclei fuse and you make helium and lots of energy. The problem is to get them to smash together fast enough, you need to make it very, very hot, 100 million degrees centigrade. And whilst we can do that, it's not really commercially viable. And keeping it going is a bit of a problem. We have ITER in the south of France. This is a hugely expensive project to do nuclear fusion on a commercial scale. That is just beginning as I speak, really. And they're expecting it to be operational by 2027. 22 billion US dollars is a cost estimate for that. So we are moving towards nuclear fusion. We're still a long way off it. It will be very expensive, but if we make it work, it will be the solution to the world's electrical needs.